Now that we've gotten our feet wet talking about sets, we're going to move into section 2.2 and talk about subsets, which are essentially just taking what we've talked about with the idea of a set, ideas of collections of things, and starting to bring into our concepts ideas that act like inequalities. So let's start off with a pretty basic example to get an idea of what's going on here. Let's say we have the set one, two, pretty basic set, 3 elements, nicest natural numbers we could ever want to see, nothing special about it. We got this set. And then let's take a look at one set that's even nicer. 1, 2. Then one set that's even worse. 1, 2, 3, 4. Really terrible. 1, 2, 3, 4. Not bad, but let's just think about these sets of numbers right now. And if you look at them, you can hopefully tell pretty obviously that 1, 2 are both in 1, 2, 3, and all 3 of 1, 2, 3 are in 1, 2, 3, 4. So it makes sense that there's some sort of language for talking about the relationship between each of these sets, because it seems like there definitely is a relationship. And that is where we talk about the language of subsets. So we say that a set A, the set A is a subset of set B if every element of A, remember our elements, fancy of saying the things that are in there, an element of B. And for this, we write A. We make this sort of symbol that looks like a flattened C and draw a line underneath it. And then we write B. So this statement reads, A is a subset of B. That's our notation. That's our shorthand. Remember, when you're thinking about math, think of it as something like a language. It's essentially just a fast way of saying, a fast way of writing, A is a subset of B. So if you look back up at these basic examples up there, you could say that this is a subset of that, and this, that one is a subset of the first one. And we can notate this going in both directions. So if we say that this is a subset of that, we would draw that little C-type term, line underneath it, say this guy is contained in that guy in a sense. And then up here, we could flip that around and say that this guy is contained in that one. Or, if we really wanted to, we could also define the relationship between these two. Really bad notation to write it sideways like that, but I hope you can tell that this one is a subset of that one. Because again, every element in here is in there, and every element that's in there is in there. Nice thing that we think of as something like the transitive property. It does sort of continue onward that way. And there's one other thing that we need to attach with this, which is that we say A is a proper subset if A does not equal B. and we denote that. A, we draw that little C symbol and don't draw a line. B. So with each of these, we could either keep that symbol there, or we could remove that line, because for both of them, this is in there, but not equal. These are in there, but they're not equal, as their cardinalities are different. They're clearly all not equal, but there are containment relations. And that's what I meant when I was referring to this sort of being like inequalities, that we would say 2 is less than or equal to 2, and 2 is less than or equal to 3, but 2 is also strictly less than. It's the same sort of thing with subsets and proper subsets. Another way of thinking about a proper subset is that, looking at that idea over there, it is a subset with smaller cardinality, a smaller cardinal. So let's take a shot at an example. So let's say that we have two sets, where the set A is going to be the set of even natural numbers less than 10, and the set B is the numbers 2, 4, 6, 8, and 10. Well, let's think about what each of those things are. So B is given, I'm not going to write that down first. A is the natural numbers less than 10. So A, if we're going to write that in roster form rather than in the set builder notation we have there, we'd have 2, 4, 6, and 8. Well, if you think about it then, you draw it out one time for yourself, you should pretty quickly tell that if you write out B, you have 2, 4, 6, 8, and 10. So, if you want to think about this in terms of that set subset notation, you could say that A is a strict subset, a proper subset of B. You can also say that A is this type of subset of B, but generally like the stronger statement where we can get it, and proper subset is a bit stronger. Let's try one more quick example on top of this. So let's say you have two sets. Let's say you have the set S, which consists of all states. So we'll say that we have the set S and we have the set C, where C is the countries in North America, and we want to see if there's a relationship between S and C. Now, let's first think about what each of those sets actually is. We'll only be given a description of S, if we want to write that out. It consists of all states. Let's say that's Alabama, Alaska, Arizona, Arkansas, California, Colorado, Connecticut, and so on. All the states. And C consists of countries of North America, so that would be Canada, the US, Mexico, I think Panama is considered part of North America, and a few other ones in Central America. But you have those countries, and we want to see, is there a relationship between the set S, states, and the set C of countries? Now, it looks like there might be, because technically all of these states are in the United States, but we're not describing this as the set of states, we're describing this as the country. So here, you have to notice that there actually isn't any relationship at all. These two don't really share anything. So, what we have here in this case is an unfortunate result where S and C don't share elements. So neither is a subset of the other. And in order to say that something is not a subset, you have the symbol S, start drawing the subset, and then like with the in symbol from 2.1, we draw a diagonal line through it to say that S is not a subset of C, and similarly, C is not a subset of S.